Hi, my name's Pete Gallagher, and today I'll be talking about using .NET Core 3.1 with the Raspberry Pi. I'm a freelance IT consultant and Microsoft Azure MVP. I've got plenty of experience programming in the IoT space. I've been doing that for many a year, all the way back to making an internet-connected Royal Mail stamp vending machine in the late 90s, so quite a while back. I also organise a few meetups. I organise NOTS IoT and co-organise .NET NOTS and NOTS Dev Workshop, and I also sit on the board of LATI, a high engineering meetup group in Loughborough. I also speak around the country on topics like this today, IoT, and I'm a STEM ambassador in Code Club volunteer too, mainly driven by the fact that I've got two naughty little girls at home who are constantly coming into Daddy's office and asking him what he's doing on the computer. So what are we going to be doing today? We'll start by looking at the .NET framework and how that ecosystem currently looks, and then we'll see where .NET Core 3.1 fits into that. We'll look briefly at how to install .NET Core on the Raspberry Pi, and then we'll spin up some Hello World console apps, first on a PC and then on the Raspberry Pi, before moving on to looking at what the IoT features are that are embedded in .NET Core for us, and we'll create a console app for that, and then we'll start moving on to connecting the whole lot up to Azure. And then finally we'll start looking at Blazor briefly, just to see how that fits and how well that works on a Raspberry Pi. So .NET framework, I guess we mostly all know this anyway, but it's a framework that allows us to, using any single language, create desktop, cloud, IoT, AI apps, pretty much anything you like. You can write in C#, F#, and Visual Basic. A little bit of history first. So the .NET framework actually started around 2002 with the first version of Visual Studio .NET. In 2007, .NET Framework 3 was released and we got WPF, which was a nice upgrade from Windows Forms. In 2012, we got .NET Framework 4.5 and Link and Async. In 2015, we got .NET Framework 4.6.2 alongside Visual Studio 2015. In 2016, we got .NET Core V1. So this was the first version of .NET Core and Microsoft's real journey into open source. This version of .NET Core did cause some problems for a lot of people, in that I think a lot of people thought maybe it was more released than it was, and then with the release cadence that was happening at the same time, there was lots and lots of breaking changes, and I think perhaps caused some problems for some people. And 2017, we got .NET Framework 4.7 as well as Visual Studio 2017. And then in 2018, we got .NET Core 2.0, and really this was the first proper version of .NET Core in my estimation. This is the version that most people will have been using just recently before moving to .NET Core 3.1. Obviously, we have .NET Framework 4.8 today, as well as Mono 6.8 and Visual Studio 2019. And so, .NET Standard, what's that? And how does that fit into .NET Framework's ecosystem? So essentially, we have some common infrastructure that sits below. So we have compilers, languages, and runtime components. And on top of that, we have base class library, core library, and mono class libraries. And they sit underneath the .NET Framework, .NET Core, and Xamarin. And so throughout that base class library, we have different versions of different framework components that are compatible with each other or not compatible with each other. And so to try and solve that problem, Microsoft decided to standardize them into one thing called the .NET Standard Library. And essentially, all of those base class libraries can then conform to a particular version of the .NET Standard. And then essentially you can write all of your same applications, but you can keep a lot of that base functionality exactly the same. Just to illustrate that a little bit more, you can see here that we have .NET Standard 1 all the way through to version 2.1. If we look on the far left hand side at .NET Standard 1, we see we have .NET Core 1 and .NET Framework 4.5, Mono 4.6 and onwards. And all the way to the right hand side we have .NET Core 3.1, which is today's release, and .NET Framework 4.8 and Mono 6.4. So what the current thinking is that if you're creating an application then try to go all the way to the right hand side of this particular table so that you can get all of the nice new goodies in security fixes in the latest version of .NET Standard and the associated .NET Core, .NET Framework and Mono. However, if you intend to create a library that's going to be consumed by applications, then you need to try and push that all the way to the left of the table. Everything from 1.0 to 2.1 is backwards compatible, but it doesn't work the other way, of course. So the lower you can make that .NET Standard number for a library that's going to be consumed, the better, the more different applications that will be compatible with. You can read a little bit more about .NET Standard there at the bottom using that link. So where does .NET Core fit into all of this? .NET Core is a free and open source set of libraries for Windows, Linux and Mac. So it's cross-platform, and this is where Microsoft is putting its development effort currently away from .NET Framework. So .NET Framework is pretty much going to stick where it is. There'll be a few security releases, and we have .NET Core currently, and then coming soon we'll have .NET 5. And so we're on .NET Core 3.1 at the moment. As I said, it's open source and cross-platform. It's highly performant, and .NET Core 3.1 is an LTS release, and so support's going to be around for a long time. So this is production-ready stuff. As you saw in the previous table, it's built on .NET Standard 2.1, and this is the only place where you're going to be able to get C# 8 as well. It's now got WPF and Windows 10 support baked in too, and so you can create WPF apps for Windows using .NET Core 3.1. Importantly for us, it also supports the Raspberry Pi. So Microsoft actually began its open source journey quite some time ago. Back in 2001, Microsoft, together with HP and IBM, sat in a room together trying to figure out the best way that they could allow developers to be able to target any platform they like. In 2002, version 1 of the .NET Framework was released, and also the Mono project began, which was an open source implementation of .NET Framework. By 2008, we had ASP.NET MVC, and that whole web platform was open sourced. And then in 2014, Microsoft went ahead and open sourced their compiler platform, Roslyn. So that was an incredible moment in Microsoft's open source journey. They also created the .NET Foundation at that point. Then in 2014, the .NET Core cross-platform project began. And so this really was their big push into allowing developers to target any platform. In 2016, Microsoft brought in the Mono project into the .NET Foundation. In 2017, we had version 2 of .NET Core released. And then in December 2018, we got .NET Core 2.2 and a preview of .NET Core 3, which amazingly also included WinForms and WPF support. So essentially what Microsoft had done at that point was to open source WPF and WinForms, which was quite a watershed moment. And then today we have .NET Core 3.1. Just looking at Raygun's example here, they were able to spin up .NET Core on the server and move from 1,000 requests to 20,000 requests. And that's just by re-implementing in .NET Core. So it really is quite a performant platform to use. I don't have the stats for .NET Core 3. I believe perhaps they'll be coming out later in the year. However, .NET Core 2, as you can see, has been on the rise. There's been over 500,000 active .NET Core 2 developers, so that's pretty cool. So, that's enough talking for now. Let's look at a .NET Core demo just on Windows to begin with. So, I've got a command prompt open, and so I'll create a directory called dnet. Nothing in it. And I've already got .NET Core installed. So if I do .NET --info, then we have up here a little bit of information about what we actually have installed. So we can see here we have .NET Core 3.1.1 installed. And then a little bit further down, you can see the runtime environment. We have Windows and then the OS version that I'm running. And then we have the .NET Core SDKs and then which .NET Core runtimes I've got installed all the way down to the bottom. And so now at this point, I can spin up a new console app just by doing .NET new console. And so that's going to restore whatever packages it needs. And that's finished doing that. And we can have a look at the code in there now. Not much in there, it's just a program.cs and a CS proj file. And so we can run that with .NET run. And there we have Hello World. So nothing dramatic, but we now have our first .NET Core console app running. We can actually have a look at that code. If we do code dot, that will open VS Code. And we can have a look at the program.cs. And so you can see there's not much to this at the moment. We're just bringing in the system library. And then a little bit further down, we have a program, a main, and we're just going to console write line hello world, which is what we saw in our console application a few moments ago. So we can close this and close that. You can actually go ahead and have a play with .NET Core 3 and specifically C# 8 just in your browser by going to microsoft.com/net or www.dot.net if you like to say something with a tongue twister in it. And you can have a play with all of the latest nice new fangdangly C# 8 features in there if you like, rather than having to pollute perhaps a work PC. So we have a Windows console app working, but really we're not that interested in that. We're here to look at the Raspberry Pi. So let's talk about .NET Core on the Raspberry Pi. Getting it installed isn't just a case of doing a sudo apt-get. Unfortunately, at least for 32-bit Linux distros, there's no apt-get. They've got one for 64-bit, but sadly nothing for 32-bit. And so there's quite a few steps that we need to do to get through that. I've actually written a blog post to take you through from start to finish, including spinning up a Blazor app and a basic console app in there. So if you hit that bit.ly up, then you can get yourself up to speed with how to do it. But essentially, we need to update our Pi, which is the first thing you should always do anyway. And then just to make life easier for myself, I've set up a shared directory in Samba. So I can just have a look at the code in VS Code directly. And then there's a bunch of steps we need to do. There's a couple of prerequisites. There's a couple of libraries that are missing from the Raspberry and distro of Linux. And then we need to download the .NET Core and ASP.NET Core binaries and runtime. And then we need to do some linking up. We need to move these binaries into a directory and then link that directory to our own profile. And then because we're going to look at Blazor, we install some Blazor templates. And then because the link, the symbolic link, is only persistent in the session we're in, we also need to modify the .bash file so that every time we start up our Pi, those symbolic links are made again. And then if everything's working, we should be able to do a .NET -- info. So let's have a look at a console app on the Pi. As I said earlier, I've set up Samba sharing on my Pi, and I've created a shared directory called share. And in there, I've got access to that from my development PC. If I make a directory in here called rpi console and go into that, then before we start anything, let's just make sure that everything's installed okay. So .NET -- info. And we get some results in there. And if we scroll up a little bit, then we see we've got version 3.1.102 on the Pi. And a little bit further down, we see the runtime environment of Raspbian. And then, just like on the Windows PC, it also gives us information about which SDKs and core runtimes are installed. And so, just like the Windows version, let's spin up a console app. And so we do .NET new console. And then in there, we should have the same lot of files. So we have a program.cs and an rpi console. And again, we can run that with .NET run. I'm actually using a Raspberry Pi 4, so it's quite speedy. It's not too dissimilar in speed when we're creating these sorts of apps to the Windows version. So there we have Hello World. And so, as I said, I've actually created a shared directory on the Pi, so that's what we're using here, so we can have a look at that code directly. And so this is my shared directory on the Raspberry Pi, and we created rpi console earlier. And if I right click anywhere in the blank space, I can open this directory in code. And just like before, we have a program and an rpi console.cs proj, and we have exactly the same program on the Pi here, so no surprise there, it's exactly the same. And so we've created a console application, but that's not really very IoT, of course. So really we need to be using some of the GPIO, the general purpose input-output of our Raspberry Pi, to flash an LED. So let's talk about that a little bit. So .NET Core has access to the Raspberry Pi's GPIO. I've wired up a small circuit to my Raspberry Pi, so we have an LED and a button wired up. There's a resistor in line with the LED to stop it from blowing up. Just delving into what's happening here, on pin 10 I've connected an LED through the resistor, and on pin 26 I've connected the button. Just a little bit about GPIO on the Raspberry Pi. There's a couple of numbering systems, so this one closest to the pins here is the board numbering system. There's another numbering system here called BCM numbering, and so we have a choice between these two numbering schemes. I prefer board numbering because I can count the pins on the Pi rather than having to get a diagram out to be able to convert between an actual physical pin and another pin number. So we'll be concentrating on the board numbering scheme here. The library we're going to be using to be able to access the Raspberry Pi's GPIO is the system.device.gpio library. And that gives us access to obviously the pins themselves, but also several different interfaces like SPI, Serial Peripheral Interface, as well as I2C and PWM and things like that. The system.device.gpio library supports Raspberry Pi as well as BeagleBoard, Hummingboard and Odroid. I've not actually played much with those. I tend to concentrate on the Raspberry Pi. It supports Linux, which is what we're using it on, and it also supports Windows 10 IoT, Microsoft's IoT derivative of Windows 10. You can install either from the CLI, or if you're using Visual Studio, then you can use the package manager, of course. You can find a bit more information here at that link if you'd like to delve in a bit deeper. So let's make an LED app. Like any good Blue Peter presenter, I have some code I prepared earlier rather than you watching me type it. So if I put that in place, I can explain what's happening. You see on line 2 here that we're using the system.device.gpio library. So really what we need to be doing is adding that using the CLI into our project. So in my RPi console app, and back in PuTTY, I can do a .NET add package system.device.gpio. And there we are, so that's finished. And up at the top we can see that's actually told us it's written to our CS proj file. So back in VS Code, let's have a look at our CS proj file. And then we can see down there on line 9 that we have a system.device.gpio package reference. So if we go back to our program.cs, we can see then on line 3 we have system.threading, and that's because I'm going to be flashing my LED on and off, and so I need a delay between an on and an off and an on. So further down on line 13, we've created a reference to a GPIO controller called controller. And you can see while I've created that new reference, we're passing in a pin numbering scheme of board, which is what I mentioned earlier. I'll leave the console.write line in place so we can see that something's happening in the console. Next, I'm going to create a couple of variables. A pin number. As we said earlier, we have an LED connected to pin 10. And then I've got a light time of 300, and that's in milliseconds. And that's how long I want the LED to be on for and off for. Next up, on line 19, we're using the controller.openPin, and we're passing in the pin number we created earlier, and we're telling it that we need it to be an output. So our LED has been driven out from our Raspberry Pi. Next, we're good programmers, so we're going to wrap our code in a try, and then we're going to spin around in a while loop. On line 25, we're writing a value to our pin of high. And then we're going to wait for our 300 milliseconds. And then, again, using the controller, we're going to write to our pin a value of low. And then wait again, and then do the whole lot again. So all we're doing essentially is pulling a pin high and low and high and low, and that will turn our LED on and off and on and off. Finally, when the program ends, we close the pin, and this tidies that pin away so it can be used again by something else. So let's see how that works. We return to our console here. We can do a .NET run. And there we have it. We can see a flashing LED on our board. So that's the first bit of IoT we've done with .NET Core on our Raspberry Pi. So let's stop that for now. So, it's all well and good being able to dial into our Raspberry Pi using a share. However, the workflow isn't ideal. We don't really want to have to be doing that. Really what we want to be able to do is develop the code directly on our machine and then push it out to the Pi. And with a little bit of messing around, I was able to get that to work. There is actually a VS Code extension that should make this work. However, I couldn't figure out how to get it to work for some reason. I did spend some time on it. But I've written some build steps that allow us to be able to do that. I've already made some code to allow us to be able to now read the value of a button to be able to turn the LED on and off. So we'll have created an LED app to be able to prove that we can drive a pin, but we also need to be able to read a pin. So I have some pre-baked code here, of course. So if I go across here to our Pi button, and we open this in code. So this is living on my local machine here. Then you can see we have some code already here. So on line 2, we have the familiar system.device.gpio. And then a little bit further down, we're still using the GPIO controller, and we've got an LED pin on 10. But we've now introduced a button pin on 26. And if you remember from our circuit, that was the pin we had our button connected to. We're opening the LED pin as an output again on line 16. And then on line 17, we're opening the button pin. And we're passing in a pin mode of input pull-up. And so what that's going to do is internally, within the Raspberry Pi, it's going to pull that line up to a high level. And when you press the button, that pin will be pulled down to a low level. And within our while loop, we've introduced a check to see whether or not the button pin is false. So as I've just explained, when you press the button, it's going to go low, which will read as false. And if it does, then we'll turn the LED on. And if the button isn't pressed, so the read results in a high or a true, then we're going to turn the LED off. And like before, we'll close the pin again. And so let's go into our launch.json. We can see here, beginning on line 27, that I've created a .NET Core launch remote console task. And what that allows us to do is spin up our code on the Raspberry Pi directly and attach a debugger. We're using Putty's P-Link here to dial into the Raspberry Pi. We're going to give it the password and the username directly. And we need to be using root because it needs to be able to gain access to the lower levels of the Pi. And we're also going to attach a debugger. We'll need to have installed that on the Raspberry Pi first. Next, if we look at tasks.json and we scroll here, we'll see we have a Raspberry deployed WSL. And what this is doing is allowing us to be able to SSH into the Pi and sync up the code. We're using rsync here. And so what that will do is it will check to see whether or not the Raspberry Pi already has a set of the files that it needs to be able to run this. And it will compare the files that we've got on our machine to the files on the Pi and only copy those necessary files. We can see that this actually depends on Raspberry Pi publish WSL. So we can see then slightly above we have a Raspberry Pi publish task, and what that's going to do is create all of the necessary binaries that we need to be able to transfer across to our Raspberry Pi. And we see this one depends on build. So a little bit further up we have our build task right at the top, and that's going to take the contents of the CS proj and build our file. And so let's see how that works, shall we? So if we return to our program.cs, we can just make sure that's all there. And on the left hand side here we have a run, and we make sure that we're using our .NET Core launch remote console launcher that we created earlier, and we should be able to hit that, start debugging, and we should see things happening then in the terminal window at the bottom. So we can see that it's restored the packages required for our new project. It's built successfully. Now it's publishing the binaries. We're publishing there for Linux ARM because that's the platform we're going to be deploying onto. Now it's copying the files that it needs across to our Raspberry Pi, and it's happy that that's done. And we can press a key to close that. And now this is it actually running directly on our Raspberry Pi. And we can see we have a hello world statement that's just appeared. And if I press my button, we can see the LED lights up. And so if I stop that code now, as I mentioned earlier, the debugger is actually installed on our Raspberry Pi, and that allows us to be able to add breakpoints into our code. So let's add a breakpoint for when we press the button. And then rerun our code. And we should see that this process takes less time now because the binaries have already been transferred across to our Pi once, and it's only just going to make sure that everything syncs up correctly. And so our code is running now, and if I hit my button, and we can see that the code has stopped. And so we can stop that code now. So at that point we have an LED flashing and a button being red, and so we have a general schema of IoT working. Although we don't really have the I of IoT, do we? We have a button and an LED, but we don't have the internet section of IoT. And so we should think about hooking this whole thing up to something like Azure. So if I close VS Code now, I've already created some code here for Azure. So if I go into RPi IoT Hub out, and we have a look at that code. And so if we open up our program.cs now, we can see that we have the usual system library and our now familiar device.gpio library. But we've also brought in the Microsoft.azure.devices.client library. And we've brought back our threading.tasks because we're going to be using delays. And we're using system.text because we're going to be using JSON. We can see on line 12 there that we have a connection string variable. We need to populate that at some point. And we also have a device client. And this is how we're going to be communicating up to Azure. So within our main sub, we've still got Hello World. But now on line 19, we're creating a device client from the connection string that we've specified on line 12. We still have our LED pin on 10 and our button pin on 26, and now we've added a variable for whether the button's pressed. If we scroll down a little bit further, we're still opening our pins, so we're going to open the LED pin as an output and the button pin as an input with its pull up. Down beginning on line 31, we've still got our while loop and we're reading the button pin, and when the button is pressed, then we're going to set the LED to be high, and if the button wasn't pressed before, then we can now say that it has been pressed, and we're going to call in to a new subroutine we've created called send device to cloud message async, and then we're going to wait for that to finish. And then a little bit further down, we're going to set the pin to low if the button isn't pressed, and set our new variable to false. If there's an exception, we're going to write that out to the console, and finally we close the pin. If we scroll to the bottom of our file, we have a new subroutine here, and this is an async task, and we've called that send device to cloud message async. We create a message, button pressed, that we're going to try to send up to our Azure IoT Hub. You can't just send the string, it must be encoded in ASCII, and on top of that it must be a byte array. On line 64, we're going to add a property to our message. In IoT Hub, you can use message properties to be able to route messages different ways depending on what's happening. Say, a temperature threshold has been breached. And then on line 68, we send our message up to the IoT Hub using the device client. Finally, on line 75, we write out to the console that we've successfully sent the message. And so, if we scroll back to the top though, currently we're missing a connection string. So we need to get one of those. To get one of those, of course, we'll need to create a IoT Hub in the Azure portal. So if I switch across to Chrome and we head to the portal, if I press the Create a Resource button, and then here in the Search the Marketplace box, we can do IoT Hub and choose the first option. Here it gives you a little bit of information about what the IoT Hub is. If we hit the blue Create button, then we get some basic information. I'm going to choose my VS Enterprise subscription, and I'm going to create a resource group. And I'm going to put that in North Europe. And I'm going to call that Virtual Azure Hub. Next we can look at the size and scale. We have a standard tier here that we can use. There is a free tier, but I've already used one of those and you're only allowed one per subscription. So I'm going to use a standard tier for now. There's some information about it here that we can look at, but we don't really need to concern ourselves with that for now. Other than the fact that we're able to send 400,000 messages a day, and it's going to cost us roughly £18 a month. We can add tags if we like, and we move on to review and create. Make sure that everything is satisfactory and hit the blue Create button. and our deployment is underway. And there we have our IoT hub has been created. So we can now go to the resource, and we have some information about our IoT hub here, and we have some menu options down the left hand side. Now the first thing we're going to need to do is allow an application to be able to read the messages that are being sent to the IoT hub, as well as send messages from the IoT hub to our device. We're going to use an application called the Azure IoT Explorer, which is part of the Azure IoT SDK. That will allow us to connect up to our IoT hub, interrogate the messages that are being sent up to it, and then send messages from the IoT hub down to our Raspberry Pi. When we start the application, it's going to ask for an IoT hub connection string. So we need to give it one of those. But first, we need to give it a policy in our IoT hub. So over here on the left-hand side, under Settings, we have Shared Access Policies. And this is where we control how our devices connect to the IoT hub. We'll see that there are already some policies created for us, IoT hub owner, service, and onwards. We're going to create one specifically for our IoT Explorer. So we can click the Add button, and then I'll call this IoT Explorer. And because we're crazy, I'm going to give it all access, and then hit Create. And that's created our shared access policy for the IoT Explorer. Clicking on that will pop out a blade with information about our IoT Explorer shared access policy, including its permissions, but also primary key, secondary key, and connection strings. I'm interested in the primary key here, so I can hit the blue Copy to Clipboard button, and then we can return to our IoT Explorer, and we can paste that in here. And hit Enter. And now we can hit the Connect button, and that will connect to our IoT hub. We can see it's telling us at the moment that there are no devices. And so that's the next thing we need to do. We need to create a device in our IoT hub which matches up to our Raspberry Pi. That device will have its own connection string that the Raspberry Pi can use to talk to the IoT hub. So let's do that now. Back in the portal, on the left hand side under Explorers, we have IoT devices. Clicking on that, we currently have no devices at all. However, we can add a new one by hitting the New button. We can give it a device ID, and I'm just going to call it Raspberry Pi. We don't need to worry too much about any of the rest of the settings for this particular demo. And just hit Save. And that's created us a device. And if we select that device, in a similar way that we had a blade containing primary keys and connection strings, we have that for our IoT device here. We're interested in the connection string here, so let's copy that. And before we go back to VS Code, we can go to IoT Explorer, and we can refresh this, and we now see our Raspberry Pi in there. If we click on our Raspberry Pi, we can actually get those same settings from within here, so it saves us actually having to go to the portal to do that. We can actually create new devices here too, should we wish. Let's go back to VS Code, and we have a space for our connection string here, so let's paste that in. And so looking at that, we have the host name, virtual Azure hub.azure-devices.net. We can see it's taken our device ID of Raspberry Pi, and it's got a shared access key there too. Again, I've got a launch and a tasks JSON that allows me to be able to run this directly on the Pi. So let's save our program, and we can hit the debug button. Make sure that we are on .NET Core Launch Remote Console. We can run the code. And so it'll build, and then it'll publish the Linux ARM binaries, and then it'll sync our files across to the Raspberry Pi, and that's done. And now it'll start debugging. So now if I switch back to our IoT Explorer, and I select my Raspberry Pi, and I click Telemetry, we can start monitoring for messages being sent from our Raspberry Pi up to the IoT hub. So I hit the Start button. Now it says it's receiving events. So if I press my button now, then it says it's sending a message on the button pressed, and there we have a button pressed message being received by the IoT hub, and we're intercepting that message in our IoT Explorer. We can press that another couple of times and we can see the same result. So we now have communications from our Raspberry Pi up to our IoT hub. So let's stop monitoring. So that's good. So the next step is to be able to send messages to our Raspberry Pi from another device, and in our case, our IoT Explorer. So let's see how we can do that. We can stop our code running in VS Code, and then we can close it, and we can look at the next piece of code. So we have our Pi IoT hub in. So let's open that up. And so we're using the same imports at the top, and we have a connection string, which we can replace because we know that now, and a device client. And then a little bit further down, we're doing the same things with our controller and our LED pin and button pin. However, now in our while loop, we have an extra call to a receive cloud to device message async routine. If we scroll down and have a look what that looks like, right at the bottom of our code, we can see that in our receive cloud to device message async routine, we're awaiting a device client message. And if a message appears, then we're going to convert that message from a binary string of ASCII characters into an actual string. And then we're going to console write line that out. And then we're going to wait for that message to complete and return back. Scrolling back up, the rest of our code's the same, so it will still send a message back up to the hub when we press the button. Once again, I'm able to debug this directly from VS Code. So make sure that we're in Launch Remote Console and we can run that. And then we're debugging. And so if we return to our IoT Explorer now, we'll notice that we have device identities, device twins, direct methods and cloud to device messages, and that's what we've just hooked up. So we have a message body here, and we can send that directly to our Pi. So we can say, hello Pi, and if I press the send message to device button, it says it successfully sent it, and then we can see received message, hello Pi. And so now we have two-way comms working from our Pi up to our IoT hub, and then from another device to the IoT hub and back down to the Pi. So we have control over the Pi. We could take this further and we could create a direct method that would allow us to be able to create functions like a reset or an update. But this is enough of an example for now. And so once you've got your information into IoT Hub, then the world's your oyster. You're able to then send that to anywhere in Azure. So we've got that working, and I mentioned to begin with that we'd look at Blazor. So let's switch back to the slides momentarily. And so Blazor. Scott Hanselman puts it quite nicely. It's a single-page app framework for building interactive client-side web apps with .Net. It's actually started life as a pet project of Steve Sanderson of Microsoft. I believe he sat on a plane and just created it while he was bored. And then he demoed it just out of the blue, and the bods at Microsoft saw it and immediately leapt on it and decided that it was the future of what they wanted to do. What it allows us to be able to do is replace our client-side JavaScript with C# instead. And so if you've got a skill set in C# there in your pool of developers, then they can make use of their C# experience rather than perhaps needing to lean on JavaScript. You write in Razor and HTML, and there's a couple of different ways of doing it. You could either use server-side or client-side, and the client-side will use WebAssembly. So I'll demonstrate both of these today. This is completely plugin-less, so it's native WebAssembly or native HTML and C#, and it's supported in nearly all modern browsers. So let's spin up a Blazor app on our Raspberry Pi. So if I return to my terminal and we go back up, I'm going to create a directory Blazor server and go in there. And we can do a .NET new Blazor server. And that will create us the framework for a vanilla Blazor server application. And that's finished doing that. So let's go back to our share directory and let's have a look at the code for that. And so we have various different directories, and I'm not going to delve too much into the code here, but we can see we have a program.cs, and in here we have the way that our Blazor server is created and started up. Now, when you create a vanilla Blazor server, it's designed to be accessed from your local host, from the local machine. But we need to access that from our development machine here with it running on the Pi. So we need to allow any IP address to be able to access our server. And we can do that quite easily by adding an extra line into the configure web host defaults call here. And we do a webbuilder.useURLs and we put a star in place of the IP address. And we're also going to be using a port number of 5000 so that we know exactly where it's going to be built and run. So I can save that. And now if I return to my terminal, we can do .NET run. And so that's our Blazor server running. And we can access that by going to the host name of our Raspberry Pi, in this case it's MS Cognitive, and then looking at port 5000. So if we switch back to Chrome, and we go to MS Cognitive and port 5000, then now we have it. Here's a Blazor app. So this is just a vanilla Blazor app straight out of the box, being served directly from our Raspberry Pi. So we can go to counter here, and we can click this and we can get the counter to increase. And there's a fetch data, and this is using an API endpoint here to be able to fetch live weather data. It's really good. It's quite a clever thing. If we actually get the Chrome DevTools open and go to network and we refresh the page, you see we don't actually get a massive amount of information coming across the wire here. We do a fetch data, and that's going to drag down the HTML for the page. And then we have some CSS, and then we have the Blazor server JavaScript, and that's what's actually going to be controlling how our web page is getting updated. In server mode, what you have is a server running on the host, and our client machine, our browser, calls up to the host server to be able to get the HTML. When something changes on the page, all the Blazor server system is doing is sending us those changes. And we can see we have some icons and some fonts, but not a great deal more. We can demonstrate this a little bit further by actually stopping our Blazor server. So if I return to my console and stop, we can see in the background that it's now saying that it's attempting to reconnect to the server. What Blazor server is doing is using Signal R to connect to our client application running on Chrome in this case. If that communication is blocked or stopped for any reason, then the whole application will go offline. And so this is one of the downsides of using Blazor server, of course, but it's still a pretty impressive framework. If using Blazor server isn't your style of thing, then we can actually do a client-side version of Blazor in WebAssembly. So let's have a look at that. I'll make a directory called Blazor WASM, and we go into that, and we can do .NET new Blazor WASM. And in order to get Blazor WASM to work correctly from the Pi so that I can access it, we need to do a similar thing in allowing IP addresses, but we can do that directly from the command line. And we do that for when we actually run the WASM application. So here we have a .NET run, and we're telling it which URLs to use, and we've put the *:5000 in there. So let's run that up, and that's running now. So it looks very similar to the Blazor server version. So if we return to Chrome now, and we refresh our page, we'll see we get a brief loading statement, and then once it's finished loading, we get our Blazor WASM website working. And for all intents and purposes, it's identical. So we can go to counter, and we can click that, and we'll get the same counting. Go to fetch data, and that's using the same API to fetch the weather data. But what is different is when we start looking at what comes across the wire here. So if I scroll up, then we get a document, so that's very similar. But scrolling down, we'll start seeing, if I pull this across a bit, some DLLs. And these are actual .NET DLLs, .NET Core DLLs. and they're being pulled down and run in what amounts to a virtual machine directly in the browser. So this is interpreting those DLLs and running our website directly in the browser. If I return to my console and stop this now, we see back in Chrome that we're still able to navigate around on our site. It's not broken like the Blazor server was. And that's because this is running entirely in our browser. What we haven't got is a facility to hit the API. That's all. But everything else is running exactly as it was before. So that's pretty impressive. That's sitting there now. I've shown you two different ways of running Blazor directly from a Raspberry Pi, and both were pretty performant. Obviously, this was just a basic web app, and I'm sure that if you tried to do anything really complicated, then you'd hit some performance bottlenecks. But for spinning up basic websites, this is perfectly acceptable. And so here's some links. There's some more information about Blazor at the top, and then you can find out information about C# 8 and .NET Core 3.1. Some information about the latest version of Entity Framework Core and Entity Framework 6.4. You can get VS 2019 and what's new about it there. That's my link to how to install .NET Core 3 on a Raspberry Pi, and you can find out a little bit more about the GPIO package there too. You can contact me at many different places, but the simplest is on Twitter. I'm at Pete_codes, or you can use at PJGcreations. You can also email me, pete@pjgcreations.co.uk. As I mentioned earlier, I also run Knots IoT, and I co-organise .NET Knots and Knots Dev Workshop and sit on the board of LATI, so you can check the websites out for each of those groups. You can also grab today's slides there at that bit.ly. And so that's about it. So go ahead, take .NET Core, and you can use it pretty much everywhere you like. I've been Pete Gallagher, and thanks very much for listening today. Thank you.